So in this video I'm going to talk about the Bolzano-Weierstrass theorem, and it says that every bounded sequence has a subsequence that converges. So let's say that we have a sequence xn, where n varies from 1 to infinity, and we know that it's bounded. It's bounded, it means that there are numbers, let's say A and B. There are numbers A and B, like real numbers, and by the way the sequence is also of real numbers, such that for all n, xn is between A and B, or in other words, like this inequality we can rewrite as xn belongs to the interval from A to B. Okay, so what we are going to do is we are going to look at this interval. So we're going to start from this interval from A to B, and we are going to divide it into two. So like let's draw a picture. So somewhere here we have A, somewhere here we have B, and let's divide the interval into denoted by C, but it's the middle, like C is equal to A plus B over 2. It's the middle of the interval. So and we are going to consider like where the terms of the sequence xn go, like in which of these half intervals, from A to C or from C to B. So since we have like infinite number of terms in the sequence, like at least one of these two intervals, from either from A to C or from C to B, contains also infinite number of terms of the sequence. So either the interval from A to C or the interval from C to B contains infinite number of xn, infinite number of the terms of the sequence, because like if both of them contain only finite number, then the whole interval from A to B contains only finite number, and this is a contradiction, of course. Okay, so now what we are going to do is we are going to again, so let's say we don't know which of the two, but let's denote this interval, the one of the two that contains infinite number. They, by the way, it might be they both contain infinite numbers, in infinite number of the terms of the sequence, in which case we pick any one of them arbitrarily. But so denote this new interval that contains infinite number of xn. Denote it, I will write denote it by A2, B2. And for convenience, we also denote like A and B, we denote by A1 and B1. So A we denote by A1, B we also denote by B1, just for convenience. So then this would be the interval A2, B2. It also contains infinite number of the sequence, so it contains infinite number of xn. So then we again repeat the same procedure. So here is A2, B2. We introduce the point C2, which is the middle of the interval, and we conclude that either A2, C2 or C2, B2 contains infinite number of the terms of the sequence xn. And we denote it by the one interval that contains infinite number, denote it by A3, B3. A3, B3. And so on. So then we continue the same procedure. So and so on. So we obtain a sequence of intervals A1, B1, A2, B2, A3, B3, A4, A4, and so on, AN, BN, and so on. So we construct this way an infinite sequence of intervals, and we notice that they're not just a sequence of intervals, but they are like each next interval is a subset of the previous interval. So so this interval, so let me remove the commas everywhere and write that each previous interval in the sequence contains the next one, or the next one is lies inside the previous one. Okay. So each next interval is a subset of the previous one. And also we notice that their length is like it tends to 0 because the length of the so the length of the length of the next interval is to be n plus 1 minus a n plus 1 is 1/2 of the length of the previous interval of bn minus an, right? So it follows from this that the length of the interval, so basically the limit of bn minus an, it is equal to 0. So now we choose, we construct our subsequence. So we choose for first, so we construct the subsequence x and k. So and k is a sequence of indices. So we choose n1 such that x n1 belongs to the interval a1 b1. This is trivial because a1 b1 is the interval from a to b, which is the whole interval containing all terms of the sequence. So this is trivial. But for the next one, n2, we choose n2 such that n2 is strictly greater than n1, and x n2 belongs to the interval from a2 to b2. We can choose such n2 because, starting from n1, there are infinite number of the terms of the sequence belonging to this interval by our construction, and so we can choose if all of them they all terms cannot be, their index cannot be less than n1 because there are only finite number of indices less than n1, and since we have infinite number of terms belonging to this interval, then we can find one that is the index of which is greater than n2, right? So and then we continue the same. So nk we choose in such a way that nk is greater than nk minus 1, and x nk belongs to the interval from a k to b k. Again, we can choose it because there are infinite number of the terms of the sequence that belongs to this interval, and only finite number of indices not satisfying this inequality. So it means that there is nk greater than k minus 1 that belongs to this interval. So and so on. So now we need to prove that this subsequence x and k it converges. So we notice that because x and k belongs to this interval, basically because of this, x and k is between AK and BK. This is for all K, of course. So because of this, so this sequence is so this sequence X and K, it is between the two sequence AK and BK, and we also know that because we previously established that the limit, because of this, because the limit of the length of the intervals is 0, the sequence, so the limit of AK is equal to the limit of BK. When K goes to infinity. And first we need to there is one missing step. First we need to prove that both AK and BK are converge themselves, but this is because they're monotone. So we notice that. So this is before we talk about their limits here. So AK is increasing and bounded from above by B, and AK is less or equal than B or B1. It's the same thing. Therefore it converges. Therefore AK converges. The same for BK. So BK is decreasing. It's not strictly decreasing, but just decreasing. So BK plus 1 is less or equal than BK. Decreasing. And BK is bounded from below, so BK is greater or equal than A. Therefore, BK converges. Okay, so we established that they converge, both of them. So now we can talk about their limits. So because the difference between AK and BK tends to 0, so the because of this, because the length of the interval tends to 0, we conclude that, and they both converge, we conclude that their limits are equal to each other. Since their limits are equal to each other, and the sequence X and K is between these two convergent sequences that converge to the same limit from this, so from these two statements, we conclude from these two statements we conclude there is such a theorem that if this holds, then the sequence converges. X and K converges, and this concludes the proof of the Bolzano-Weierstrass theorem, because that's the subsequence that we needed to find.